the organizing committee for inviting me to give this talk. I did it for two reasons. One, I wanted to use the word selenochronology. The other is that I wanted to, for myself, sort of wrap up the things that have been happening in the last couple of years, and I hope this is as helpful for you as it was for me. So this is not maybe our Bible anymore the way it used to be, but I certainly do recommend it to you, the Scientific Context for the Exploration of the Moon document. It's really well written, and it also wraps up a lot of the state of lunar science at the time that it was written, and so what we're trying to look at in this talk are the top three that just happen to be all about craters and chronology and things that this committee deemed to be very important to lunar science. And in 2009, both at the LRO targeting workshop and at this meeting, in fact, we were talking about how LRO in particular and LCROSS as well might address some of these issues in impact cratering and chronology in particular. The things, you'll see this over and over again, the things that always come up are the moon as a laboratory for understanding the impact process, and thanks to Jim Head, I don't have to spend much time on this. He gave a great overview of understanding the impact process from understanding lunar impact craters. And what I'll focus on today is how the moon preserves a temporal record of the Earth-Moon bombardment flux. This is something that turns out to be really crucial, especially for the early origin of the Earth-Moon system, is what was coming in and bombarding that system at the time that they were formed and shortly thereafter, and particularly at the time that, say, on the Earth, our continents were forming and life was arising. And if there was a bombardment around that time, how would that have affected both planets? The moon preserves those craters, obviously, so we can use those as a proxy. So what progress has been made since we had those two meetings? And that's what I'll be talking about today. This is, I tried to be fair in wrapping up some of the work that's been done. I don't claim to be complete, so please don't crucify me if your work isn't included in this. So origin of the impact melt rocks themselves. Impact melt rocks are our best way to understand when a crater formed. They were formed in the impact itself and largely reset in most of their isotopic systems. And so by studying the age of those impact melt rocks, you can get the age of the crater itself. If you do that from multiple impact craters, you build up a bombardment history or a flux. Those impact melt rocks, we sometimes have a very simplistic view of how and when and where they formed in a crater, and maybe that they're all the same. What LROC and Mini-RF have been showing us is that that assumption may not be the best one. So what I'm showing here is this crater, one of the craters that Veronica Bray looked at and mapped out some of the impact melt lithology distributions inside the crater, and all I want to show you is that it's non-uniform and that there are different kinds. There are flows and ponds and veneers and all sorts of things going on in this. Now this is a pretty small crater, and this may not be applicable to all craters, especially large complex basins, but it does show us that there is, and it's not a simple system. You can't really assume it's a very simple system. And then in addition, these LROC images are showing us that large deposits, such as the sculptured hills, and Paul Skoudas looked at this, the sculptured hills gave us the Apollo 17 poikilotic impact melt breccias, which we have canonically taken to be, to give us the age of the Serenitatis Basin. These were specifically sent to find the age of Serenitatis. Well, these sculptured hills, when you look at high-resolution geologic images, are more widespread than the Apollo 17 site, and Paul argues that these may actually be Imbrium rocks, in which case all bets are off for the age of Serenitatis. So the geology is showing us that things are complex in a way that we thought they would be, but without the high-resolution images didn't have to face up to. New sample ages come out all the time. This is a very vibrant field. What I wanted to focus on here were a lot of 3.9 and older ages. One of the holy grails of impact melt rock dating is to find these old impact melts that predate, say, a lunar cataclysm or a late heavy bombardment. Some of the most recent work that's been most interesting that shows us 3.9, well, shows us a lot of 4.1, 4.2, 4.3 billion year old ages come from non-impact melt rock samples. And yet there's some question as to what could have created these rocks with these intermediate ages. It's too young for the canonical age of the lunar magma ocean, and it's too old for the canonical age of the lunar cataclysm. So these intermediate ages are really interesting. In particular, the granulitic breccias, we think those are metamorphic rocks. They have ages around 4.1, some of them. Zircon overgrowths, we think those form when a zircon gets dumped back into a hot magma, and zircon rims form on that pre-existing grain, 4.3 and 4.2 billion years old. Some Apollo 16 regolith samples have been redated, and these are breccia samples, just whole rock breccia samples, and some of them are anorthosites. Some of them have impact melt lithologies associated with them, but they're not totally impact melt rocks. Some of those come out at 4.2. Here's a Faroan anorthosite that Lars Borg dated as part of trying to understand the lunar magma ocean, and yet it came out at 4.3 billion years old, which he thought was odd and may not be the lunar magma ocean, maybe some later metamorphic event. So we're seeing these intermediate ages, but it is kind of a little difficult to interpret them as basin-forming impacts or impact ages at all. We know that they're metamorphic ages, but what was going on the moon at that time, we have very little record. Additional insights from some of these samples, particularly those Apollo 16 anorthosites that have some of those old ages, and some basalts that we're finding, is that there are young ages recorded in them too. And when you do some very careful high-resolution argon work, you can get diffusion ages, so partial reset ages. If you crystallize a rock and then subject it to low-level metamorphism, some of that argon will diffuse out, not all of it, and so you'll preserve the old crystallization age, but you can also get the young disturbance age as well. It's kind of similar to your lead-lead or uranium-lead systems. Those are showing heating events at 3.3 billion years, so much younger than the canonical age of the cataclysm. Basaltic meteorites are much younger too, and those of course record the age of the basalt flow, but those are going to provide absolute ages for crater counts if we could find a match between the composition of those basaltic meteorites and basalt flows on the surface of the moon. You could correlate those as well. And some of these zircons that are showing up not only have these old ages that I showed before, but some of them have young ages, 3.4. So these might be showing us evidence of impacts that are younger than the cataclysm as well. Okay, moving on from samples, new crater counts are coming out. People are jumping all over improved resolution images from both LROC and digitized lunar orbiter images, and counting craters down to very small sizes in ways that couldn't have been done before these high-resolution images were returned. Most of these are showing that when you look at very small crater bins, you find more craters, or you count more craters than the model age was previously assumed to have been, or the radiometric age is for samples where you know their provenance. And so this has been interpreted as contamination by secondaries. We know this is a hot topic on Mars when we found out that secondaries were everywhere and may contaminate your crater counts at very small sizes, and particularly for very limited terrains in aerial plan view. So it's a cautionary tale that we don't fully understand the calibration crater curves, including secondaries. It's not a closed topic in the community on how to account for secondary craters. And so when we're looking at very small areas or very small craters, there's some caution to be drawn there. Some people are revisiting old crater counts. There's a debate going on in the literature right now between the Strom and Malhotra group at University of Arizona and Chook et al. Strom came out with a paper some time ago saying that morphologically fresh craters on the moon have a size frequency distribution similar to near-Earth asteroids. And what this shows is that the recent population of material hitting the moon and the Earth by extension are from near-Earth asteroids, whereas the lunar highlands have a size frequency distribution similar to the main belt, which argues that the main belt asteroids were the source of ancient cratering, including probably the late heavy bombardment. Chook et al. Came out with a paper in 2010 that argued that, in fact, the class 1 craters have the same density on the whole moon as they do on the Oriental ejecta blanket. And so that argues that they were formed right after Oriental, which means during the late heavy bombardment or in the tail of the late heavy bombardment. And so there's a debate going on in there. That debate really centers on how can you combine crater counts from different units on the moon. How can you define, or how can you tie a morphological characterization such as a class 1? Class 1 just means it's morphologically fresh, but does that mean it's young, or does that just mean it's well preserved? So what is the preservation state versus age, and what are those characteristics? Can you use those to infer ages? And again, how do you count for secondaries, particularly in the small sizes? So this debate is not closed. I think the papers on this will still be coming. But even beyond that, even if you could count craters perfectly, you still have to tie them with a calibration curve. And now our calibration curves are coming into question. There are some very recent models that our approach for our crater curves have been very empirical, using our known radiometric ages and tying an empirical fit to those with the crater counts on those surfaces. What people are doing now is using the asteroid belt, using models to smash the asteroid belt up, and then delivering that material to the Earth-Moon system and predicting what the crater calibration curve should be, and comparing that with our crater counts. And that's had some pretty good successes. It's also had some surprises. One of the things that comes out of this is there's a real anisotropy between sort of the leading edge and the leading hemisphere and the trailing hemisphere of the moon, and also the polar regions and the equatorial regions of the moon, and those occur for different dynamical reasons. It's not very much of a difference, but especially when you're delivering asteroids from the asteroid belt, you can see that difference. And so that sort of says, well, when you're crater counting an area, you can't combine it with crater counts on the other side of the moon, because they're not going to be the same, even if they're the same age. They're also dealing with the issue of small craters, undercounting small craters, overcounting small craters. It could be that when you make a crater into porous regolith, like we have on the moon, the megaregolith, as opposed to bedrock, maybe you erase those more quickly, and so you don't have those around to count. Some of the results from this estimate Oriental and Caloris to be about 3.73 billion years old, which is a little bit different from what we had empirically. But then even if you go further than that and say, well, even if we had a model of the current asteroid belt, is that really the source of these impactors at all? Well, maybe the current asteroid belt wasn't even the source. So people are going even back further into the origin of the solar system and saying, really, what was the source? So there is a model that shows that even large asteroids get broken up and dumped and ejected from the asteroid belt, and there was much more mass earlier in the asteroid belt than there is now, which maybe we hadn't really given much credit to. We thought maybe the asteroid belt in the past was more or less like it is now. But it may be different by a factor of 3, which would affect, even if you had a constant delivery rate of impactors, if you had more in the past, you'd get more impactors coming in. And so that is something to think about. And then sometimes we may not even know what the source is at all, because there's no remnant of it. And Bill Bakke has made a model with this E-belt of asteroids, which is an inner asteroid belt, or on the inner edge of the current asteroid belt, that may be the source and may be completely gone by now, and we cannot see it anymore. And so these are really getting at the origin of the solar system and the evolution of early bodies in the solar system that can even be delivered, that can even be crater counted now on the moon. We continue to look in the terrestrial record for evidence of impacts in the terrestrial record. There's been a little bit of progress in this area as well. We know now that there are terrestrial spheral beds all over the place. Several groups have really done a good job looking for these and trying to stratigraphically date them on the Earth. And so there are several of them sort of throughout recent history. None of them are particularly old, but this may help us understand the flux on the more recent Earth. There is a paper out there that says that the Ischio rocks, their metasedimentary sequence up in Canada, their iridium content and the ratios of some of those siderophile elements is too low to be reconciled with a huge pulse of asteroids coming in. You'd put more iridium in there than you can really see in those rocks, and so they argue that it's a cometary input, and we've been talking about input from delivery from the asteroid belt in this talk, and there's very little modeling about what kind of cometary sources would be there and what kind of evolution in the cometary source there would be. And there are new techniques being developed. So in addition to our normal arsenal of, say, isotopic techniques, the Arizona group is developing uranium, thorium, helium specifically for terrestrial impact melt rocks, having good success with that. So there's some work to be done in this area as well. So in conclusions, lunar chronology, to me, I think is getting more interesting. Some may say that is getting more complicated. Some of our very simple assumptions that we've been able to make throughout the years to understand some of our results are being called into question, including the sample ages themselves, the crater counts, the crater production functions, and even the early history and population of the solar system. But of course, to me, there's always hope. That means there's always work to do, which means there's always funding to be got, we hope, including using these new remote sensing data sets, not just LRO, but all of our fantastic data sets that are out there, orbital data sets, to really map out some of these lunar geological boundaries. I think that's going to turn out to be critical. Where do you end your crater counts? And that is probably multiple data sets, not just optical, but some of our mineralogical maps as well. We can continue to do high-resolution image-based crater counting, relating these to location, keeping in mind the subtleties of the difference in crater populations on the asymmetries. Improved understanding of the regolith thickness and understanding of the crater formation process and modification process in regolith in a porous unit. And GRAIL is going to really help us understand the global variation of that unit. Tying the sampling of impact melt rocks to the lunar impact flux itself. If we have an impact melt rock, how do we really know where it came from? And if we don't really know where it came from, what is that age telling us? Using improved techniques such as that uranium, helium, magnetic fields, diffusion studies, more isotopic analysis on existing samples, we have a very rich sample set here on Earth already, but that doesn't mean that we don't want more. In particular, sample return from key benchmark craters that will really help us pin down some of these points on that lunar crater curve, in particular the South Pole Aitken Basin, which is the oldest, deepest visible basin on the moon, that would really give us an old tie point for that lunar production curve. This was not selected in the last New Frontiers round, but it was called out again in the 2013 decadal survey, so it is still there. It is still a very high priority. It came in at one of the highest priorities of the Inner Planets panel, which I think speaks to its importance for the whole inner solar system. Thank you.
Lots of time for questions. Brad Jolliffe.
Wow, you're to be commended for covering so much territory in one talk. It's amazing. For those who aren't really clued into all of the geochronology, though, there may be a sense of some confusion based on, the more information we get, the more complicated it seems to be, and the geochronology seems to be approaching the geology in terms of real complexity. Could you say just a little bit about the different methods, just focusing on age dating samples, the different methods and what they are telling us that's different, and where we need to be going with either additional analyses or, well, you actually made the point at the end that it's not just dating more samples, it's getting samples where we know the provenance. But talk just a little bit about the different dating methods.
Sure. So I didn't talk about all the good work that's been done in dating lunar impact melts and the things that we think are really solid, and so maybe that set you up for a lot of confusion. But we do very well understand many isotopic systems for dating impact materials. So argon, rubidium, strontium, samarium, neodymium, uranium, thorium, lead. All of these samples, all of these techniques tell you something different about the history, the crystallization, and the thermal history of the sample. Did you want to say something, Jim?
No, sorry.
Oh, okay. And so you can bring all of those systems to bear on any particular impact melt rock and get a good history. And we have many samples that are like that, where we really do understand the crystallization age and the thermal history. And when we look at those, we really do think we have dated some impact melt rocks very well. You can do this for more. All you're doing with samples that you don't know where they came from, say a lunar meteorite, all you're doing there is building up a statistical flux over the whole moon and not really tying it to a specific basin. So I'm hoping that with the combination of new isotopic methods and better isotopic methods and new geologic mapping, maybe we can do a better job relating some of our existing samples to specific structures. Conversely, we can build up a larger history of the moon statistically, or we can go get new samples that we know where they came from.
Jim Head.
Yeah, just to continue on with your last point there, which is we can go get new samples that we know where they came from. So, some of our work in the Oriental Basin, as Paul Warren was asking at the end about the interior, strongly suggests that there's like kilometers of impact melt there, and I mean maybe up to 10. Okay, so these things we've been modeling essentially what happens when you take different crustal columns and melt them and then differentiate them, and so we'll report on that at the next LPSC. But the point is that we may be having a new destination here where we can go to impact craters that have excavated the central melt columns of a whole series of these big basins and then actually look at the diversity there. And it may be that if you've got some mantle material incorporated in this, that you're going to have some really interesting differentiates. Plus, you can certainly date the basin from that. So that ranges from South Pole Aitken Basin to Oriental and everything in between. So I think that's a really new destination that we should think about.
I agree, and I think I broaden that to just say impact basins that have exposed central melt sheets, I think are one of your best bets. Oriental is one of those, SP is one of those. There are others.
Bill Balke, last question.
Thank you. That was a really nice overview, Barb. Let me ask you about one of the samples you talked about. You said there was a particular fan rock that had an age of 4.36, and you said originally people thought that was from the magma ocean, and now they're less sure. At the last LPSC, I saw Lindy Elkins-Tanton talk about how tidal forces may be able to keep the magma ocean alive much longer than we would have thought, and so things close at a much younger age than we would think. Could that be a possible explanation, or do we need something else?
Oh no, absolutely. I think that either tells you something new about the dynamics of the magma ocean and the longevity of the magma ocean, if that is a magma ocean cumulate, or it tells you something about a metamorphic event sort of in that mid-region of lunar history. Now, it's really difficult to tell. It's just a crystallization age of a rock. It doesn't tell you what event that crystallization is tied to. But either way, these are interesting ages.
Yeah, I agree.
And if the magma ocean, another point is if the magma ocean really did persist that long, could that have provided a heat source for some of these metamorphic events that we're seeing? Are really these metamorphic events only impact events? We don't